Hello again and welcome to lecture number 4 in this module on sensors for the course Electronic Systems for Sensor Applications. We are talking about the history of how the field of MEMS started and where we are today. The reason we are doing that is because many of the sensors that you will use these days are made using MEMS technologies. In the last lecture we saw how the field started in the late 1960s. And we saw the journey until the early 1990s, which is when many of the first MEMS products started hitting the market. In this lecture, we will see all the developments that have happened since that time, and then we'll conclude by looking at the state of the art of where things are today. So let's get started. This is the slide that we paused at in the previous video. If you remember, I was saying that in the early 1990s, many of these first MEMS products started becoming a reality. The silicon inkjet printheads were primarily being pushed by Kodak in the early 1990s. Unfortunately, that technology no longer exists because it has been wiped out by other digital technologies. Analog devices started coming out with the first MEMS products. So here is a SEM of the first accelerometer and then the first MEMS gyroscope that was made at this company way back in the early 1990s. And this here is a photograph of something called as a digital light projector. This was a technology started by Texas Instruments, which is used in projector devices used for making presentations. A very important development here started in the late 1990s. Agilent is perhaps a name that is familiar to many of you. Many of you may have heard of this company called as Keysight, which previously used to be called Agilent. That company spun off from Hewlett Packard, right? HP, again perhaps a name which is very familiar. And Agilent was making RF test equipment, devices and so on. And their chip making division spun off as this company called Avago in the early 2000s. Now, Avago is perhaps the largest company that you are very much affected by, the technology you use on a day-to-day basis, but many of you may not even have heard of this company. So, we will know more about them in this lecture. And the reason they impact your life is because they came out with this device called as an F-bar. So, here you see a grain of rice and there are 4 F-bar chips placed on one grain of rice. This is called a film bulk acoustic wave resonator. So, that is an acronym. In short, it is called F-bar. These are used to make filters. So, in your cell phones, you have a lot of filters because you are working in a very crowded spectrum. You have a lot of different radios and when you have that, you need very, very good filters so that you do not have interference from one protocol to another. So, Avago came out with this technology. And when the smartphone revolution started in the late 2000s, this technology really took momentum, and we'll know more about that in a little bit. But let me sort of talk more about accelerometers for 2 reasons. One, like I said, they are relatively an easier device to understand. The principle of operation is not that difficult to understand. The fabrication and the design of these structures again are relatively easier as compared to maybe other sensors such as microphones and gyroscopes and so on. And moreover, there are many applications where these sensors are used. So, you perhaps are very familiar with the consumer applications. So, free fall detection in your phones, camera stabilization, interactive gaming again in joystick like devices. You would have experienced all of these first hand. Indoor navigation is something that is gaining momentum these days, primarily with virtual reality headsets and so on. But there are many other applications. Now, automotive again is perhaps you have experienced through airbags, right? So, airbag deployment systems again use accelerometers for detecting crashes and accidents. A lot of applications in aerospace and military and in industry as sort of heavy industrial applications as well as shown here. All right. So, again we will look at one of these as a case study. So, we will use the automotive systems as a case study and then we will talk about the origin of airbags in automotives and how MEMS sort of took that place in this industry. So we'll look at a brief history of airbag systems in cars. Now the electric car, or not the I should not say electric car, the motor car is again a very old technology. It goes back to the 1940s and even before that. Airbags did not make their debut in cars until much later. So the rudimentary patents for airbags started coming out in the 1950s. In the 1960s, really, there were the first kind of prototype systems that were used to deploy airbags, but the commercial acceptance came much later. So in 1970s, the Ford company started experimenting with this technology, and General Motors as well started piloting this in some government use applications. But the first commercial car that any common man could buy only came out of this company. Again, this is an American automotive company, on the Oldsmobile Tornado in 1973. So this is a photograph of the car. This had the first commercial airbag deployment system. And in 1988, this again is a commercial application out of an American automotive company. These started being offered as standard equipment. So Chrysler started selling cars that had airbag systems installed in them as standard equipment. So you need not pay for them as an extra option. In 1994, TRW, which is a tier 1 OEM, they started producing gas inflated airbags. So these are what are used today in most cars. And TRW started using the accelerometers that were being made by analog devices. So if you remember, I mentioned that analog devices started coming out with their first products in the early 1990s, and you can see that parallelly sort of this airbag industry is also shaping up, and this was a case of the companies being in the right place at the right time. So in early 90s there was enough work done by other companies for TRW to develop enough confidence in airbag systems, and also analog devices had enough confidence in MEMS to start coming out with MEMS accelerometers. So very naturally there was a partnership that formed here, and this is something that has grown, and even today all cars use MEMS accelerometers for their airbag deployment systems. Now how do accelerometers work? Here is a very simple illustration. We will talk about this in more detail in the next set of lectures, where we look at some practical challenges in accelerometer applications. So there you would need to understand more about how these are designed, how these are fabricated, what fabrication variations could lead to what sensor specification level errors and so on. So when we talk about them, we will discuss this in more detail. For the time being, we will just stick to this very simple illustration shown in this slide. So what is shown here is a mass spring damper system, and then if you pull this mass with a force, you can describe the motion of the mass through a second order differential equation. Now assuming you are just applying a DC force, you get a DC deformation in the spring. So a constant force, or if you pull it and then just hold it pulled by a certain amount, the restoring force in the spring is the stiffness of the spring or the spring constant multiplied by the deformation. All right. Now here, for example, this perforated object you see here is the mass. So that's the proof mass or mass in this diagram, and you see there are some folded structures here. These are the springs. So we'll understand more about how do you make springs out of such folded structures in the next set of lectures. For the time being, maybe you can just take it from me that these are the springs that are shown here, and the damping is because of air damping when this structure vibrates. All right. So this SEM shown here essentially can be represented by this free body diagram, which is shown here on the right. Now if you take such a structure, put it on a chip, and the chip accelerates, right, you can imagine this being similar to a case where you are sitting in a bus and the bus starts accelerating. So you feel a fictitious force pushing you in the opposite direction, right. Similarly, now if this chip were to accelerate, the proof mass would feel a fictitious force because of the acceleration of the chip, which is the external force that acts on the proof mass in the chip frame of reference. All right. So, that deformation in the spring multiplied by the stiffness of the spring is equal to the mass of the proof mass multiplied by the acceleration that the chip is experiencing. So, the acceleration can then be written as a product of the stiffness, the deformation divided by the mass. So, if you measure the deformation, you could estimate the acceleration, because assuming that you designed this structure, you would know what mass you have designed for. If you design these folded flexure springs, you would know what K or stiffness you have designed for. So, if you could measure the deformation x, you could estimate A. So, this is like the gain term. The K divided by M is the gain term or the scale factor or the sensitivity term in the accelerometer, and what you need to do is come up with an electrical circuit that can measure x. There are many other points mentioned here, which we will come back to maybe towards the end of this module when we talk about some practical challenges. So, now how do you detect this x? Here I mentioned if you can measure this x electrically, then you can estimate A. So, we perhaps need a way of converting this x or the deformation of the mass into an electric current or a voltage or something like that. All right. So, that is what is called as capacitive transduction. You may remember that I used this phrase in the beginning of the previous video. Transduction refers to conversion of energy from one domain to another. So, here we are referring to electrical and mechanical energy domains. So, transduction would refer to converting from electrical energy to mechanical energy and also mechanical energy to electrical energy. All right. So, now we can split that into two terms. So, conversion of electrical energy into mechanical energy is something called as actuation. So, actuation is also a form of transduction. Capacitive actuation uses a combination of an AC signal and a DC signal to generate motion in a mass spring damper system. So, I have shown the mass spring damper that is shown in the previous slide in a different form here. So, this is the mass spring damper system. Here you have an AC and a DC source that are connected across these two plates of a capacitor. All right. So, one plate of the capacitor is a fixed plate, this plate will not move, and the other plate of the capacitor is formed because of the proof mass. So, when the mass moves, this plate moves. So, the capacitance of this capacitor changes. Now, you can hold the potential of the mass, the electric potential of the mass to ground. Remember, these are all silicon structures. So, you can simply make an electrode contact to the silicon and hold that at ground potential. And on the other plate, again where you have an electrode, you could apply these voltages across the capacitor. All right. So, we go back to the previous slide. You see a lot of these comb structures here, right. So, those combs form those plates of the capacitor like I had mentioned earlier. We will study such a structure in much more detail in the later lectures in this module. All right. So, how do you convert then from electrical energy with a combination of DC and AC voltages to mechanical energy? Let us look at that. So, when you have a movable capacitor and you apply a potential difference across its plates, you have a force between the two plates of the capacitor, right. So, the force is given as the spatial derivative of the energy stored inside the capacitor, the potential energy. The potential energy in the capacitor is half CV square, where C is the capacitance and V is the voltage that you have applied. Note that this is a partial derivative with respect to the gap between the plates. The voltage is a function of time, all right, but it is not a function of the plate distance. So, the partial derivative only then applies to the capacitance, whereas the voltage term comes out here. The capacitance is given as epsilon naught A by D. When you take the derivative with respect to D, you get a D square term in the denominator, and then you have a V square term here. Now, remember, V is a combination of a DC term and an AC term. So, you get DC plus V AC sin omega t squared in the V squared term. So you can imagine this has this is like a plus b squared. So you get a squared, b squared and a 2ab term when you take a sum of or square of a sum. Now the vdc square term has no component at omega, it is a dc force. The VAC square sin square omega t term has two components. One is a DC because sin square omega has a DC component and a 2 omega component. So again, no component at omega, but the product term gives you a component at omega. So the product term is what is shown here. The half drops out because you have a 2 in front of the VDC VAC sin omega t. So you get epsilon naught a divided by d square VDC VAC and then a sin omega t, which I have not written here because this is the amplitude of the force. So this force is a sinusoidal force at the same frequency at which you have applied this sinusoidal AC voltage. So now if that frequency matches the resonance frequency of this structure, you get vibrations of that structure at resonance, alright. So that is how you convert from electrical energy with these voltages to mechanical energy, which are vibrations in these structures. How do you write down an expression for the vibration amplitude? So if you are vibrating at resonance, the vibration amplitude is this force amplitude divided by the stiffness of the spring multiplied by the quality factor of the resonance. So the springs, remember, are these folded flexures here. The quality factor depends on this damping, alright. So if you package this chip in vacuum, then you get very large quality factors. So for very small voltages, using a very large quality factor, you can still get very large displacements, okay. But in an accelerometer, this is not what we use. The actuation is used in other devices such as gyroscopes. In an accelerometer, we are mainly concerned with sensing displacements. So that is called sensing. So sensing again is a form of transduction. So this is called capacitive sensing. So the capacitive sensing is done with a much simpler circuit. So now ignore all of this thing here on the left and just focus on these things here on the right. So again you have a gap closing capacitance with two electrodes. One is a fixed electrode and the other is a moving electrode because it is part of this proof mass. Now you do not need any AC voltage, you just need a DC voltage which is connected across the plates of this capacitance, right. So again you hold the proof mass at ground potential and you apply a DC potential to the fixed electrode like I have drawn here. And now you have a current that flows across the capacitance through this circuit when the capacitance changes, because remember the charge on the plates of the capacitance is a product of the capacitance and the voltage that you have applied across it, and the current is time rate of change of charge. So again the voltage is independent of time, so the partial derivative with respect to time only applies to the capacitance, alright. And I can write this as a separation of variables. So I get dc d gap and d gap dt, alright. So dc d gap we know from what we derived earlier is epsilon naught a divided by d square, and d gap dt is the velocity, right. So you get the current flowing through the circuit is as a function of the velocity of the proof mass. So if this is harmonic motion, then you get a j omega term and then you get the displacement amplitude, alright. If it is not a harmonic motion, you measure the velocity by measuring the current and then you integrate that to get displacement. Now when you work with the comb drive like structure, this expression is a little bit different. We will look at what this would be like in the next lecture, but this expression holds for something like the cantilever, where the gap between the two plates changes, the two plates of the capacitance, the gap between them changes, alright. So the comb drive has a little bit of a different expression which we will cover in the next lecture. Okay, so now we have looked at capacitive transduction, where earlier we covered actuation. So this is how you generate a force between two plates of a capacitor using voltages. So you are converting from electrical energy to mechanical energy, right. You are causing displacements in a proof mass. In an accelerometer you do not need this. In an accelerometer you only need these, because remember the displacement comes because of external acceleration. When your chip accelerates, the mass deforms or the mass moves because of the fictitious force it feels in that frame of reference. So, there you do not need to cause any vibrations yourself. You are interested in measuring the deflection of the mass because of the external acceleration. There you just need a DC voltage source, and this is an expression that you get. And what I mentioned was this is true for what I called as a gap closing capacitance, where the gap between the plates of the capacitance changes when the mass moves, which it would in the case of a cantilever like device perhaps. But in a comb drive based device, that is not what happens. The expression DC-D gap is a little bit different. So, we will look at what that would be like in the next lecture, alright. And there you will see you do not get a velocity term, you get a direct displacement term. Now, capacitive transduction is very popular because you do not have to make any contacts to the proof mass. So, the proof mass can be very pristine, and this is called action at a distance. All of the transducers, which are these electrodes, are not in physical contact with the structure. So, you can preserve the high quality factors of MEMS resonators and get, because of the high quality factors, for example here, you can get very small voltages to cause very large displacements, alright. So, that makes capacitive transduction very attractive. The other thing is you can do it in a silicon platform. So, there you can leverage all of the benefits of using CMOS compatible processes and keep the manufacturing costs really low. Alright. So, the other device I want to talk about is a much more complicated structure to understand. This is called as a gyroscope. To understand how a MEMS gyroscope works, let us look at this illustration first. This is Foucault's pendulum. Again, if I am sure you have seen this many a times before, and the gyroscope uses this particular thing called as Coriolis acceleration that a mass moving in a rotating frame experiences, right. So, we use the Coriolis acceleration of the mass to detect rotation, right, which is what is done in a gyroscope. So, how does that work? We will use this animation that I have picked up from Wikipedia, the link is given here. In the first panel, you see an observation made from an inertial frame. So, the blue disc is rotating, there is a red observer, this red dot on the blue disc, right, and there is an object which starts out from the center of the disc and moves linearly, right, towards the edge as seen here, right. So, if you are making this observation from an inertial frame, you would describe that the mass moved in a straight line. But from the perspective of the red dot, so in the rotating frame, you see the red dot and the mass are offset by 90 degrees from each other, but initially the mass started moving towards the red dot. So, in the red dot's frame of reference, in the rotating frame, the mass starts moving towards it, but then deflects and goes in this direction as shown in this animation. So, that you can describe again in the inertial frame, the mass is just going in a straight line because of some force which is pushing it in that direction. But in the rotating frame of reference, to describe this motion, you need to invoke this fictitious force. So, that is called as the Coriolis force, which I talked about in the last slide. The Coriolis force uses a product, a cross product of the rate. So, that is the rate at which this blue disc rotates, multiplied by, or a cross product with the velocity of the black ball in the inertial frame, alright. So, these two terms give you the Coriolis force, and again when you have a force acting on an object, it results in deformation of the object, and the deformation, like you saw in the last slide, can be sensed as an electrical current, and that is how you can estimate then the rate of rotation and use this device as a gyroscope instead. So, here is another animation which illustrates the same thing. Imagine a proof mass vibrating in this axis, and when the world rotates, you see the motion has a component along the orthogonal axis as well, because the velocity along this axis, cross product with a out of plane rotation vector, gives you a component of force acting along the orthogonal axis to what is shown here. So, all of these motions can be described by a set of two different second order differential equations. The mode 1 is the first mode of vibration along this axis where I am moving this cursor, and mode 2 is along the other axis where I am moving the cursor now, alright. And these two are coupled by the Coriolis force, as you can see here. So if you keep one of the axes actuated, like shown here, under the influence of Coriolis force, you get deformation in the other axis. So that is how a MEMS gyroscope works. These are two modes of operations in which you can use a MEMS gyroscope. One is by measuring rate, which is through Coriolis force, like I just showed, and the other option is to use it to actually measure the angle of deflection, right, where you call this as a whole angle gyroscope. What it translates to is different structural sort of manifestations of these devices. These are a little bit advanced concepts to cover in this course. So if you are interested, you may go check out primarily work out of Farooq Ayazi's group at Georgia Tech. Their group works on both kinds of gyroscopes, and there are many other groups that work on this technology as well. All right, so I spoke a lot about silicon capacitive MEMS, but then in the beginning of the previous lecture, I also mentioned that there is a device called an F-bar made by this company called Avago, which is used in every smartphone out there. That is a piezoelectric device, so the principle of operation is very different compared to silicon. Now piezoelectrics, as perhaps you are aware, are materials where you can apply an electric field and generate strain or deformation in the material, right? So you can use that in two ways as shown in these illustrations here. One is where you can make electrodes laterally on top of the piezoelectric film and apply a electric field essentially along the x-axis, right? So along the parallel to the film, and using that you can generate deformations in along the direction of the electric field or even orthogonal to the direction of the electric field. Or you can do what are called as thickness mode devices, where you create a sandwich. So the piezoelectric film is sandwiched between two electrodes, and you apply a field in the vertical direction and generate deformation again either in the vertical direction or in the orthogonal lateral direction. So this is how piezoelectric devices work. The F-bar devices, this photograph I had shown earlier, where you have 4 F-bar devices kept on a grain of rice, are used to make filters, right? So here are the filter transfer functions of these aluminum nitride F-bar filters made by Avago. Avago went on to buy this company called Broadcom. So Broadcom, I'm sure, is a company all of you have heard of. Avago bought Broadcom, but because Broadcom is more popular than Avago as a brand, they retained the name Broadcom. As you can guess, because these devices are used in any cell phone, this company must be manufacturing a large number of F-bars every year, which is about more than this number of F-bars every year. So it's a really large number of F-bars. An interesting statistic, so when the first iPhone was introduced, Avago stock was trading at $5 per share. You can perhaps guess that now they must be doing really well because of this device, and this is where they are today, right? So this is about, so the day this was recorded, the stock is about $300 or so. So this one device has made that company so much successful, and in terms of market value, the F-bar is perhaps the most commercially successful MEMS device that is out there. If you have used Alexa, right, Amazon Alexa, you have used another piezoelectric MEMS device, which is a MEMS microphone made by the startup called Vesper, right? Their microphones are used in the Alexa home automation devices that are sold by Amazon. And there are many, many more startups now in the thin film piezo MEMS space. So remember I said in the early 1990s there was this community that was forming around silicon MEMS. Now that is starting to happen around piezoelectric MEMS, all right. So here is just a snapshot of some of these startups that operate in this domain and some of the foundries that offer access to piezo MEMS processes. So to summarize, I would like to conclude with telling you about where we are now. All right, we saw how the field of MEMS originated, how the journey was, and let us conclude by looking at where we are today. So there are many, many large companies that are doing MEMS. All their names are listed here. I spoke about some of them, like Analog Devices and Broadcom, Honeywell, and so on. But there are many other names here that I'm sure you will recognize. There are many small startups as well, and you can see all of them are doing really well because they have been acquired by larger companies, and Vesper is that startup I just mentioned in the last slide. There are many fabless companies also that use global foundry technologies to get their devices made, right? So Global Foundries is an example, TSMC is an example of a foundry that offers processes, and there are many companies that utilize them to make products and then sell them. And there are many emerging applications primarily in piezoelectric MEMS around low power sensors. So ultra low power gyroscopes is something that people continue to actively work on. Microphones, as you can guess, right? Chirp Microsystems makes ultrasonic transducers. So all of these are upcoming applications. There's many more in the space of LiDAR and then using metals to do again inertial sensor kind of applications. So with that, I would like to conclude this lecture. I hope the last two lectures gave you a flavor of how the field of MEMS has originated and the dynamics that have gone into the shaping of this field in the last 30 years or so. In the next set of lectures, we will take the accelerometer as a case study and then use it to illustrate some of the other concepts that I want to cover, such as practical challenges in building and making sensor systems. Thank you.